Welcome to another MOOC live session, welcoming your questions on any subject in astronomy.
All right, the first question is, we've covered this before a little bit, but it might be a good time to update it. Do you have any recommendations for good books on astronomy?
Wow, so big general question. I would say every year, since I write popular books, I sort of know the market. Every year there are probably 50 or 60, high quality popular books on astronomy. Most of those, of course, are on a subject, a topic in astronomy. There's been a spate of books on exoplanets and life in the universe because that's a booming field. There's usually a handful of good cosmology books every year. It's actually unusual that the general astronomy books at the popular level, but not textbooks, that's actually a small niche. That's generally only one or two really good ones a year. Maybe there's half a dozen in total. I don't have any particular one to recommend. However, a couple of years ago now, the book that went with the Neil Tyson's Cosmos reboot, so Cosmos was rebooted by Neil Tyson, and they wrote a book to go alongside that TV series, and I think the authors are Neil Tyson and Don Goldsmith. I can't remember the exact name of the title now, but if you search on them as authors, that's a good book, and it stands alone from the TV show. You don't need to watch the TV show. Good visuals, clear explanations, covers the subject pretty well. That's the best single book I would recommend right now.
All right, the next question is from one of our live viewers who asks, I am having trouble understanding the simulation hypothesis and why one of your three propositions that you mentioned must be true.
Mm-hmm. Okay, well, so I'll have to rewind on the simulation hypothesis. It's a premise that comes out of the field of philosophy, actually. So it's a conversation about the far future of life in the universe, or even our form of life. So the simulation hypothesis is basically, in a nutshell, is the idea that we could be fully simulated entities, that your perception that you're living a real life as a biological sentient being is false, because in fact what's happening is we're living in a simulated reality created by a higher level civilization, advanced aliens. And the premise for that is not ridiculous, given that humans, with their still quite new computer technology, are creating virtual reality of better and better quality. Obviously, virtual reality or simulations that we use for gaming are not totally realistic yet, but think of how much more realistic they are than a few decades ago. So the simulation hypothesis just argues that we're unlikely to be the most advanced civilization in the universe, or even this galaxy, or even this part of the galaxy, and then an advanced civilization, as we do, would create simulated entities as their sort of playthings, or just for recreational purposes, or just because they could. And if those simulations were sufficiently realistic, it might be hard to tell the difference between a simulated reality and the real thing. Now, this simulation hypothesis also makes a second premise. That's the first premise, that advanced entities could create simulated creatures that were indistinguishable from biological ones. The second part of the premise is, of course, a tricky one, because it assumes it's what's called substrate independence. It's the assumption or argument that your brain, your conscious thought, your sense of self, your sense of I, is not dependent on the gray matter in your brain. It's not dependent on your biological status as a living organism, but could be simulated in a computer, in silicon, if you like, in a computer, purely computationally. So some people will not accept that premise, and for them the simulation argument falls apart before you even make it, because they just don't accept that you could have conscious sentient being independent of a biological creature. But if you accept that it might be possible to create a simulated conscious sentient entity in a computer, then the simulation hypothesis arises. And the argument is that
it turns off air mass.
Sorry, we had some noise in our corridor. We're not in a totally pristine environment here. We're in a busy building full of researchers and students, and some of them are noisy. So the simulation hypothesis then makes three statements and argues on purely logical grounds, if you accept the two premises that I just made, one of them must be true. Either most creatures or entities that are able to make simulated entities self-destruct before they're able to do so in large numbers. So evolution beyond our state of technology or intelligence essentially is unstable. So hardly any advanced civilizations exist who could make simulated creatures. That's one premise. And that is entirely plausible because humans are at an unstable part of our technological progression where we have nuclear weapons that could blow us all up many times over. And that's still true even after the Cold War. There's thousands of them. Or we could take the planet and destroy it through toxins or biohazards or whatever. So one of the three premises is that that happens and that technological civilizations just don't get beyond a certain point because they're unstable and they all self-destruct. Or the second argument is that essentially none of these suitably advanced civilizations that they could do this choose to do it, that they somehow make a choice not to do it, even though they have the capability or the potential to do so. And on the face of it, that seems an unlikely premise too, because, well, we do it. You know, we are real biological organisms, but we like to create simulated entities in our games and virtual reality. We watch TV shows and movies, which we try and make as lifelike as possible. So that's the second premise, or second argument. And the third argument is that we're already living in a simulation. It's already happened, and it's us. And by simple logic, if you accept the two prior premises, one of those three arguments must be true. And the question is, which one do you like? And I've already given you mild arguments against the first two statements. And the third statement is we live in a simulation. Objections to the simulation hypothesis, apart from its underlying premises, are that it just seems outrageous. I mean, some people just think that it just seems such a crazy, outrageous argument. But it is based on our current technological situation and a projection or an extrapolation of where that's headed. And so it's not entirely unreasonable. It's a plausible premise. And of course, the premise here is that the simulation would be indistinguishable from reality. So video games are obviously video games. But this is, and then we're not even talking about The Matrix or the movie The Matrix and the idea that's based on. There are no glitches. This is not like bad computer software. This is seamless. And so there's no way we'd be able to tell. So it's a very provocative argument, the simulation hypothesis. And one of the architects of it, Nick Bostrom, philosopher at the University of Oxford, who, he's one of the philosophers who's addressed the underlying logic and plausibility of the argument. When he's asked personally what he thinks the odds are that we live in a simulation, he assigns it a probability like 10 or 20%. So not very low, not very high, but not very low either. He has a good sense of humor and a somewhat ironic form of delivery, so it's maybe a little hard to tell what he actually believes. What I believe, I think the odds are actually very low. I think it's an intriguing argument, but I don't really buy this for a second. But could I disprove it? Can I disprove that I live in a completely high-fidelity simulation? Of course not.
All right, the next question is from Jeremy, who is on with us live, who asks, I'm really curious about astrostatistics and the state of quantitative research in astronomy. Can you talk about the state of this field and future work?
Sure. Astrostatistics is a sort of subfield of astronomy. Astronomy has always involved statistics. So even if you get back to very basic things like measuring the position of a star many times, you will not always measure the same position with any measuring device or telescope. And the distribution of those measurements will follow a Gaussian or normal distribution. So astronomical measurements have often random errors, and the statistics of those random errors is well understood from mathematics that go back 150 years. Modern astrostatistics sort of extends those very simple statistical arguments that are used throughout science into a different realm, because astronomy, of course, is now dealing with big data sets. So what astrostatistics these days does, in addition to various foundational things like error analysis, is it also tries to deal with underlying distributions of quantities where they're hard to measure. And so you're making models, mathematical models, and you're populating them with simulated data or fake data or model data. And you do that statistically because you generate large amounts of simulated data to populate some diagram or some set of quantities that you want to diagnose in the real universe. And so people use statistics that way. They also try and do statistics of very large numbers of objects. So we have surveys now, we have galaxy surveys with hundreds of thousands of galaxies in them. The Gaia survey is going to measure the positions and measure some information on roughly 1 billion stars in the Milky Way. And so you have, huge statistical tests and tools that have to be applied to data sets where you have 1 billion objects. So astrostatistics is a pretty interesting area because people are using various methods. One of the most popular methods is based on Bayesian statistics. Bayes, B-A-Y-E-S, is a famous mathematician. I'm not going to remember exactly when he lived, but he tried to make statistical tests where you didn't know what the underlying distribution was. If you have a measurement where you think you have any reason to believe the errors are normally or randomly distributed, then they will follow a distribution defined by Gauss, the Gaussian distribution. But there are measurements where you don't have that expectation or basis. And so Bayesian statistics is an attempt to model errors and statistical distributions without any assumption at all about the underlying nature of the distribution of errors. Essentially, you let the data speak for the errors as well as for the data itself. So that's a very popular way to proceed in astronomy, because in many cases in astronomy you can't do an experiment. It's not a lab situation, so you have no measurement that's going to tell you what the underlying statistical distribution of your measurements is. You have to let the data tell you, and you want to make as few assumptions as possible. Astrostatistics has its own journal. There's a major international conference and probably a handful of other conferences every year in that subject. And most major astronomy departments will try and have at least one faculty member with extremely strong sort of mathematical statistical training who can act as the expert for the faculty in that department.
All right, the next question is from one of our live viewers who asks, how long do you think it will take to get a human on Mars?
So that's an interesting question because a lot of people are talking about it now and trying. The players, of course, are the countries that are involved in the space activity, in the space program, and a couple of private sector new entries in the private space program. As far as countries go, NASA makes its plans public and visible. There's no secrecy in NASA. And so NASA has retooled many times in the last 15 years its plans for sending astronauts beyond Earth orbit. Mostly those plans have gone in the backward direction of pushing off the time that might happen just because of budgetary constraints. About 15 years ago, NASA had a Moon, Mars, and Beyond plan, which would have put a man on Mars or a woman on Mars by about now. Well, obviously that didn't happen. So the current plan of NASA is sort of staged exploration of the Moon as a stepping stone to Mars, which is sort of the way Moon, Mars, and Beyond operated too. An increasingly sophisticated set of Mars missions that will culminate in sample return in probably 7 or 8 years, and probably 7 or 8 years past that, the first humans visiting Mars, but for a very short period of time, perhaps a week or maybe 2 weeks. It's a long way to go for a couple of weeks, but it's a big mission to put them there. So they won't be making a habitat or anything like that. So if you added up those numbers, that's 15 or 16 years. So we're talking about 2030. So that's the best guess for the US. Russia really doesn't have the means to go to Mars. Their space program is poor. Russia as a country is, now, if it wasn't for nuclear weapons, they'd be kind of a second world power at this point based on economic potential, and they can't function in space very well at all. China has committed to going to the Moon and to Mars, and their timescale is very uncertain, but given their rate of growth of their program, maybe 7 or 8% a year budget growth for their space program, they could do it in the same timescale, and they could in fact beat the US to the punch by getting there in the late 2020s. Then we come to the private players, of which Elon Musk, the head of SpaceX, who said he wants to die on Mars, and not entirely facetiously. SpaceX has plans to go beyond its orbital delivery, carrying freight to orbit and then astronauts into orbit, to a Mars vehicle. And of course, Elon Musk had a press conference just last year where he showed off, simulations and sketches and artist renditions of a very ambitious vehicle that could rocket assembled in orbit that could carry hundreds of people to Mars to service a colony. He didn't really venture a timescale on that. In Musk's most aggressive timeline for SpaceX, he might get there about the same time these two countries that are thinking of it do, around the late 2020s or maybe at the earliest 2025. So we're talking about at least a decade before any human sets foot on Mars. There are a couple of other private space ventures that are talking about going to Mars, but they're not powerful enough players with firm enough plans that I'd venture a time on that.
All right, our next question is from a live viewer who asks, actually I think this was a previous live session, is there any influence on the cosmic microwave background from galactic structures between us and the CMB, or from anything that has passed through it?
Yes, it's a good question. The microwave background radiation is a relic, is an imprint of the early universe. The radiation started to travel freely through the universe when the universe was 1,000 times smaller and therefore 1 billion times denser than it is now. So a redshift of 1,000, 400,000 years after the Big Bang, roughly. And so that radiation, when we look at the microwave sky, is essentially a picture of the infant universe when it was a tiny fraction of 1% of its current age. But as that radiation travels through the universe, it's of course subject to influence from the structures of the universe that exist before it gets to us. And that includes clusters of galaxies and large mass concentrations. So those microwaves can be subtly distorted by gravitational lensing. Photons are subject to gravitational lensing. So any large structure along the line of sight where for the microwave photons coming to us can affect them. The biggest imprint on the microwave photons comes within our galaxy because there's ionized gas and plasma in our galaxy, and the microwaves can interact or scatter with that plasma. And it's actually the structure, and then there's dust in our galaxy. Mostly microwaves are immune from dust because they have very long wavelength, but if there's very large amounts of dust, they are slightly subject to it. So it's the galaxy imprint, the foreground, if you like, because the galaxy is very close. The galaxy parts are tens of thousands of light years away as opposed to billions of light years through the universe. The galaxy imprint is probably the most tricky part because it has to be removed from the observation of the microwave background to talk about cosmology. And if you recall the claim of polarization of the microwave background from a South Pole experiment about 1.5 years ago, there was evidence taken as evidence for inflation. That claim, very exciting at the time, actually fell apart. The instrument was called BICEP2. That was the acronym. The BICEP2 claim, which got everyone very excited, actually was retracted a few months later because the signal they thought was an imprint of inflation, very early universe physics, on the microwave background was actually the imprint of our own galaxy, much closer. And that was like a big oops in science because they were pretty embarrassed to have made a false claim. It's difficult work, so I think people cut them some slack for that. So yes, the microwaves that travel through the cosmos everywhere are indeed impacted by physics much closer to home, and that actually is a significant problem and obstacle in interpreting that radiation cosmologically.
All right, our next question is from a live viewer. They asked, I'd like to know why there are no missions going to the moon anymore. Have we learned everything we could about the moon?
So there are some missions going to the moon. There haven't been any in the last year, and I don't know if there are any this year, but if you go back a little further, there was a time 4 or 5 years ago when there were a handful. There were actually 5 different moon missions. Several of these were the missions that uncovered water on the moon. So there was a set of news stories 3 or 4 years ago, great excitement because these small orbiting missions had detected spectroscopically frozen water on the moon. So the moon does get some attention. It hasn't got attention very recently. And part of the answer is yes, we do know a lot about the moon. At Johnson Space Center, there are, I think, 452 kilos of moon rocks. It's a lot of moon rocks. That's whatever, 1,000 pounds roughly of moon rocks in a biohazard level 4 containment center in vacuum, protected. It's even hard to go see them. I visited and was able to look at the piles of rocks, but obviously you can't touch any of them. So with all those moon rocks, we've learned a lot about lunar geology, but not everything. For example, we have not completely cemented the story that the moon formed from an impact of a Mars-sized object on the Earth early in its history. We would actually have to go back to the moon. The rocks we have not completely cemented that story. So to learn if that really happened, we probably have to go back to the moon to different sites and bring back rocks. I think the moon will probably not get much activity until two very ambitious things start to happen. One is the construction of a moon base, and it's obviously an easier place to set up a base and a habitat than Mars, because Mars is 8 months away and the moon is a week away. So rescuing astronauts or ferrying supplies is much easier. And I think there will eventually be a moon base, perhaps an international one, so we can learn how to work in space well beyond Earth orbit. And then the other one is a space elevator. In technological terms, it's possible to build an elevator from the surface of the moon with basically a gossamer thin cable, but very strong cable, some carbon nanotube type material. And you play that cable up to the point where the weight of the cable is balanced by the centrifugal force of the spinning moon, and the cable just hangs there in space. It has to be stabilized somehow, but it's sort of like an Indian rope trick. That kind of a thing would allow you to launch things to zero gravity and move around the solar system with no cost of rocket fuel, for free, because you'd use little solar-powered lifters going up and down the cable. And a space elevator could be built with existing technology. It's a difficult project, but not impossible. Price tag probably $5 or $10 billion. So when one of those two things, the elevator, space elevator, or the moon base, get sufficient critical mass behind them, the moon will suddenly become a hive of activity.
All right, the next question is from a live viewer who asks, what do you think about VSL, variable speed of light theories?
So variable speed of light theories are not really just one thing. It's a sort of grab bag of theories, some of which are designed to explain things that relativity, Einstein's theory of relativity, was designed to explain in a different way. And you can understand why, because the premise for special relativity, for Einstein's theory of relativity, is that the speed of light is an absolute constant. So no matter what your state of motion or rest, you always measure the speed of light to be the same. And by making that very strong assumption, you get special relativity, where time has to be a variable quantity, length is variable, and mass changes as well with the speed of relative motion. As a way of sort of doing away with this bizarre behavior of mass, space, and time, variable speed of light theories just say that the speed of light is not a constant, either that it varies according to your relative motion, or perhaps that it's varied over cosmic time, or perhaps that it varies with region in the universe. There are variations of all those things in the theories. So is there any evidence for any of these theories? And the answer is no. All we can do at the moment is lab physics for the most part, and no lab physics experiment where speed of light can be measured extremely accurately to, I think, the 10th decimal place now, or 10 significant figures, has ever found the speed of light to vary depending on situation. We'd love to do these experiments further than the Earth's surface, and so there are various timing experiments that can be done, especially in the solar system and occasionally beyond, but they're not at the level of precision to test these theories. So at the moment, the answer is these theories exist as alternatives, basically, to relativity, but none of them has any evidence for them, and some of them are hard to test even in principle.
All right, the next question from a live viewer is, what would we see if we passed the radiation emitted by a black hole through a spectrograph? Would black hole spectroscopy yield anything useful?
So the radiation in question is Hawking radiation, the discovery or prediction, if you like, of Stephen Hawking from the mid to late 70s is that the black holes are not immune from the laws of thermodynamics, and therefore they have a temperature. So black holes are fairly simple objects with a mass, a spin, and according to Stephen Hawking, a temperature. When you calculate the temperature of a black hole that the mass of the sun, an object that would be about 3 kilometers across, that temperature is, I think it's nano-Kelvin, so 10 to the minus 9 or less of a single degree Kelvin. That's an impossibly small temperature. It's way beyond any astronomical measurement. So no one's ever detected Hawking radiation. It's not even clear if we could. If you did detect it, however, and were able to disperse it into a spectrum, what you think you would see is a black body spectrum. So the sort of classic black body curve that you'd see if you took human radiation in the infrared or reflected light from the Earth in the visible. That's the premise. It's a thermal spectrum, essentially.
All right, the next question, again from a live viewer, is could you please talk about the status of our understanding of fast radio bursts? How likely would you say, from what we know so far, that this could be an artificial phenomenon?
Yeah, there have been a couple of articles in Science magazine and one in Nature in the last few months. These fast radio bursts are, bursts of phenomenal energy because they come from sources that are often very far away, billions of light years away. And these bursts are very rapid and somewhat irregular. So there's not like a pulsar situation where it's like a metronomic radio signal reflecting the rotation of a neutron star. These are much more energetic situations because they seem to be coming from external distant galaxies. So they have enormous luminosity and they don't strictly repeat, and there'll be a series of bursts and then they'll go quiet. So people are really speculating to what's going on. The best type of object to explain this are obviously black holes. Black holes present the most intense gravity, and so matter falling into a black hole or being compressed by a black hole can generate, intense bursts of radiation. The black hole is rotating, so those bursts might have some periodicity or quasi-periodicity. And why they come out at radio wavelengths, that's also unclear at the moment. So the best guess, and it's really only a guess, is that these are stellar cataclysms that lead to the fast radio burst, something along the line of gamma ray burst situation, so hypernova, if you like, do you want to call it that? But because the bursters are so far away and because these signals are not very well defined on the sky, we're really very unsure of their nature.
All right, the next question is, do you think Hollywood is getting better about using quality scientific facts instead of just making up stuff?
Yeah, that's a good question. I think so. I mean, we've had a spate of movies involving black holes, for example, Interstellar or whatever, or space travel, where they've really made an attempt to get it right. The Martian is another good example. So the last couple of years, I've actually seen more than a handful of films, and they've nicely done well at the box office, which is gratifying, where they've apparently made some effort to get the science right. Another recent example is Hidden Figures, which is the story of the unsung heroines in NASA, African-American women who are working in a very difficult situation for them in the South in 1961, who were employed by NASA to do calculations, because computers were very primitive at the time, as part of the first orbital science for the early astronauts. It's a nice movie. It's based on a book that didn't get as much attention as the movie is getting now. And that's also a movie that really tried to stick to the facts. In fact, the math, which is presented, I just saw it a week ago, about the orbital calculations is actually pretty accurate too. Not that every blackboard filled with equations was physics, but they really made an attempt to get it right. So it seems that there's a recent trend of really pretty good science movies where they make some serious effort to get the science right, which is heartening. But you know, for every one of those, there's a handful of science fiction movies where, you know, lip service is paid to the science, and there's a lot of essentially impossible things happening.
All right, so the next question is from a live viewer, and they want to know, can we believe all of the information we get from NASA and ESA? For example, the probability of spacecraft crashing, or data from the search for life on Mars, or anything else.
Yeah. So what's the quality of the data from these big space agencies? The European Space Agency is NASA's counterpart in Europe, based in Garching. Oh, sorry, actually based in Noordwijk, which is in Holland. Generally, yes. I mean, first of all, these are government agencies. The ESA is an inter-European intergovernment agency of Europe, and NASA is a federal agency. And they are all subject to open records laws and data requests that have to be satisfied from journalists, from members of the public. They often have websites that are open, which include a lot of data. I mean, there's a lot of data that's hidden just because it's so arcane, detailed, and enormous that no member of the public would reasonably want to see it or know what to do with it. But in general, they're not secretive. The quality of the data, you know, depends on the application. NASA and ESA, you know, have to do some very difficult things. They have to make some models of things that we barely understand. And so in that case, maybe the data is not perfect because they're trying to do something very difficult with it. But if it's data about an orbital trajectory or the mission plan for one of the facilities they've launched into Earth orbit or beyond into the solar system, those data are extremely accurate because they have the best tools for the job. NASA and the European Space Agency, they don't have the world's most powerful supercomputers. You don't actually need the most powerful in the world, but they have enormously powerful supercomputers deployed at multiple locations to do a lot of the routine calculations of these missions. No one else is going to get a better answer. So the quality of the data is pretty good. Obviously, slip-ups have happened. There was a famous case about a decade and a half ago where a space mission was lost due to miscalculation of the metric conversion from inches and feet to centimeters and meters. That's pretty embarrassing. What's embarrassing that anyone is still using English units, as those are called. But those situations are actually pretty rare. Generally, NASA and ESA data is very good, very high quality, and very reliable.
All right, the next question is, if a neutron star is destined to become a black hole by absorbing material from a companion star, then what happens to all the neutrons? Where do they go when the core collapses into a black hole?
Yeah, that's a good question. So a neutron, say you formed a neutron star. So you had a massive star that died as a supernova. The core collapse squashed the material so that the protons and the electrons merged, sort of a reverse of beta decay, forming neutrons. Because the neutrons have no electric charge, they can sit very close to each other like eggs in a crate. And so you've essentially formed an enormous atomic nucleus with an atomic number of 10 to the 57 because it's a massive star core. So that's a neutron star, and that would otherwise be where the situation ended. The star will be spinning too because the original star is spinning and angular momentum is conserved. But if that neutron star forms as part of a binary system, subsequent evolution can add mass to the neutron star. And as the question implied, it's possible that that added mass siphoned off an existing, maybe even a less massive star, because it obviously lived longer than the neutron star, could push the neutron star over the boundary or the barrier to a black hole. And that barrier is about 3.3 to 3.4 times the mass of the sun. So if that happens in principle, what actually happens to the neutron star? Well, what happens to the neutron star is steadily, because this is not happening all at once, but it's happening steadily, that mass is added. At some point, the additional mass squeezes the neutron material, the pure neutron material, to the point where the surface gravity is sufficient that light can't escape. In other words, you can calculate what the escape velocity would be at the surface of a neutron star based on how much mass is within that radius. And at the point where that exceeds the speed of light, you have essentially turned the surface of a neutron star into an event horizon. And at that point, the material becomes invisible to the rest of the universe. It would be a very interesting transition to be in a spacecraft around such an object, watching material siphoning onto a neutron star, which is a physical object that you could see if you were up close, and suddenly that neutron star winks out and disappears from the universe as the neutron surface being compressed turns into an event horizon, hidden from the rest of the universe.
All right, the next question is, will there be any mining missions to the oceans on Europa in the near future?
Unfortunately not. It's a European probe, a true probe of the interior of Europa would be a fascinating mission, a super high priority for any astrobiology work, given the likelihood or the plausibility that the European oceans contain biology. So the mission that's been approved for the early 2020s, Europa Clipper mission, is not going to do that. The Europa Clipper is mostly an orbiter. The most adventurous it gets is it's going to drop, it's going to have a metallic mass, a metallic object, projectile, as part of the mission. And it will hurl, as it orbits Europa on a close pass, it will hurl that metallic object onto the ice pack and hopefully spit off some icy material, icy and rocky material, into orbit. And then as it orbits, as the spacecraft continues to orbit Europa, it will sniff that material or the vapor resulting from the impact with the spectrograph and try and learn what the European ice is made of. Is it salty? Does it have, it's not going to detect microbes in the ice, but what can it learn about the ice and therefore the oceans of Europa? So that experiment will be done, and we'll know the answer in roughly 9 or 10 years. The next step of doing a lander on Europa and somehow melting down through the ice to see what's in the oceans with what usually is called a hydrobot, that's been on the drawing board for 20 years. NASA had a plan for that a long time ago, and it's unfunded, and it's not part of the Europa Clipper mission. It would have to be a separate mission. Well, my bet is that a private sector company, a space exploring entrepreneur, one of the billionaires like Elon Musk, could dust that plan off and fund it, fully fund it. It would probably cost a couple of $1 billion, and there are a handful of billionaires who could get together and do it. But it's not in the plan right now, even though the engineering studies have been done. So it's very far off, at least 20 years off, basically.
Okay, our next question from a live viewer is, what manipulations are required to make information from telescopes into a colored image if we only have a series of ones and zeros from CCDs?
Good question, because it's to the heart of astronomy and how research turns into pictures you see on the internet. So the full story is the light comes in through the telescope, passes either straight into a camera and camera optics or through a spectrograph and is dispersed into spectra and then into the camera. The CCD camera is sealed in a vacuum, is kept at liquid nitrogen temperature, and the light hits the CCD surface. Now, even on a large telescope with a fairly large field of view, CCDs, until a few years ago, they were rarely larger than a postage stamp. Now they're maybe the biggest is about the size of a playing card. So the CCDs and there are many, many millions of pixels on that size. So that material is usually silicon, and the photons coming in are converted into electrons within the silicon, and it's an array of pixels, a two-dimensional array, and then the charge is read out along the rows and then along the columns. And so with a series of electronic registers or indexing devices, the photons, which have been converted into electrons, are read out along an electrical wire. And so photons have been converted into electrons. The electrons on each little picture element or pixel are read out at a slightly different time so we can keep track of them. And then those numbers are essentially available for further analysis. When you want to make a picture, you basically just take that string of numbers that you got by counting electrons on the CCD substrate, and you just turn that number into an intensity. If you want to make, and that would normally just be a black and white image where the highest intensity is white and no light is black. If you wanted to make that a color image, you'd actually take multiple exposures through different pieces of colored glass. The exposure you took through the blue piece of glass would be counting the blue light from that object in the same way by counting electrons and turning it into an intensity that you could then make a graph of or an image of. And then it would do that for a blue, a red, and a green filter. And with data from those three filters, essentially combined mathematically according to a simple weighting scheme, you can generate the illusion of true color from what originally were just photons and which were just transformed into simple electrons on the CCD.
All right, the next question is from Desmond, who is on with us live, who asks, could you explain what are Lagrange points and why it is a good idea to send spacecraft there?
So Lagrange was a French mathematician, mathematical physicist. Thinking it's the early 19th century. It's at least about 150 years ago or so. And his field was orbital dynamics. So he was one of the pioneers of figuring out how things move around in space. And in particular, not just the simplest situation where there's one object orbiting another, like the moon orbits the Earth or the Earth orbits the sun. He was interested in the more complex situations where there are 3 or even 4 bodies. The Lagrange points are stable or unstable balance points. They're places in a gravity situation where the gravitational force from 2 objects in different directions balances out to create no net force. And so if you are in such a position with no net gravity on you, then you don't move. Your position is stable. You're not being tugged or moved or accelerated in a particular direction. So if we consider the moon or the Earth orbiting the sun, there are Lagrange points between the Earth and the sun. That's the most obvious one, because there's naturally a balance point between the Earth's gravity pulling away and the sun's gravity pulling towards the center of the solar system. But there are also 3 other Lagrange points. And these are all gravitational balance points. And the reason they're important in space, in the space activity, is if you can position an object at a Lagrange point, then it's not going to move. And so it can stay in a fixed position, do its science, do its survey, do whatever mission it's going to do with a very small expenditure of rocket fuel, as opposed to, for instance, something in low Earth orbit where it might stay up there for a while, but at some level you're going to need rocket fuel to boost its orbit because there's drag from the atmosphere at that level.
All right, the next question is, do you think that helium-3 will be difficult to obtain from the moon?
So helium-3 is an isotope of helium. Helium is 2 protons, 2 neutrons. Helium-3 is 2 protons, 1 neutron. And so it's an isotope, but it has essentially the chemical properties of helium, because that's always determined by the atomic number, which is the number of protons. So it's a light isotope. And on Earth, the way first of all, helium is hard to get on the Earth. I mean, the repositories of helium, many of which are deep underground, are finite. And helium-3 is a trace ingredient. It's a rare isotope of helium. And on Earth, you would have to use some sort of centrifuge type technique or diffusion technique to separate out the lighter brand of helium from the heavier brand of helium. And that's fairly inefficient, and there's not much helium on Earth, so that's going to be time consuming and expensive. Helium-3 is used in various industrial processes, various catalytic processes, and so it's in fairly high demand in our modern industrial society, and it's rare and expensive on the Earth, which has led people to wonder whether we might not get it more cheaply or more readily from the moon. On the moon, helium is not that much more abundant on the Earth, but there are processes that take place on the moon's surface because of the radiation that hits the Earth's surface that produce helium-3 naturally. And so the lunar surface has a composition that includes a higher concentration of helium-3 by far than you would find on the Earth's surface. So people have said, yeah, let's go to the moon. Let's mine helium-3 on the moon, and it'll be easier and cheaper than getting it on Earth. It's not clear that that's true. First of all, mining on the moon is not anything we can do now. And also, we don't even know if we'll be so dependent in industrial terms on needing a supply of helium-3 10, 20, 30 years from now. We might have new technologies that mean we don't need helium-3. But helium-3 is certainly available on the moon, and that has made people make fairly serious proposals to mine it and bring it back because it has such value.
All right, the next question is, we know that black holes can attract things around them due to huge mass and density. How come jets of electrons, or how come jets are ejected from black holes?
So black holes are indeed black, and their gravity is such that neither light nor anything else can escape. But black holes are also spinning because they formed from a normal star. A star like the sun is spinning roughly once per day. And so if a star like the sun collapses by factors of hundreds of thousands or millions, then that spin rate is going to go much higher, to many times a second. So we expect and understand, although no one's ever actually measured the spin rate of a black hole, except very indirectly, that black holes are going to be spinning very fast. So now what happens is that when a black hole accretes matter, or sucks in mass from the surrounding medium or from a neighboring star, that's a typical situation in a binary, then that mass is of course compressed and generates a lot of energy. It tends to go into the equatorial region of the black hole and form an accretion disk. And the plasma that results from this very hot gas that's sort of in a swirling region around the black hole is more free to escape at the poles of the black hole than along the equator. And so from this material in the accretion disk, it's quite natural in physics, and simulations show it too, that jets of plasma will scoot out, not carrying away a large fraction of the mass by any means, a small fraction of the mass, but because the plasma is moving at very close to the speed of light, it creates spectacular effects. I mean, it's got enormous, each of those particles has enormous energy. So we do have evidence that black holes create jets. We've seen that in black holes in our own galaxy. We've seen it more dramatically in supermassive black holes at the center of other galaxies. And so the jets that black holes make are ways that material does not escape the event horizon. That was material that was never inside the event horizon. That was material that was in the accretion disk and never really got into the black hole, but on its way towards the black hole was funneled up through bidirectional jets into a relativistic plasma.
All right, our next question is about amateur astronomy, and it is, amateur observations are a cool hobby, but could you talk about possibilities for amateurs to take part in real scientific projects, and/or what are good research projects for amateur astronomers?
Right. It's a broad question because amateur astronomy equipment at the high end is overlaps significantly with professional astronomy. That's true both in terms of the telescopes, because there are a number of amateur astronomers that have meter scale telescopes, and that's the low end of research telescopes professionals use. And every amateur astronomer has available charge coupled devices, or CCDs, and the best amateur facilities cool them with liquid nitrogen and really have essentially or almost research grade CCDs. So these are really powerful facilities. In terms of the projects they can do certainly supernova discovery work by imaging nearby galaxies and having a large catalog that they return to every night. They can find exoplanets by monitoring stars and looking for the occasional dips caused by a transiting exoplanet. They can do important work using filters on nebulae to diagnose the gases and the excitement by gases of high energy radiation from stars. That's kind of survey work that big telescopes don't tend to get to do, so amateurs can help with that. There's a whole set of projects, too many to say actually. The Astronomical League is a loose umbrella organization for amateur astronomy societies around the country, and their website gives a pretty good sense of what amateur astronomers are up to. Another amateur astronomy tradition that is very venerable, I think goes back over 100 years ago, is the American Amateur Astronomer Variable Star Organization, AAVSO. And that there are amateur astronomers, you know, well before there were CCDs, when they were just using photographic plates, were monitoring variable stars. So that's a job requiring patience. There are over 40 different types of variable stars with very different signatures and different astrophysics causing their variation. And amateur astronomers can make a real contribution in that field, because a lot of these stars are not so faint they can't be seen with a half-meter telescope or something like that. There are also citizen science projects. So Galaxy Zoo is another place I would send amateur astronomers. Galaxy Zoo is, of course, mostly citizen science using existing data sets like from the Sloan Digital Sky Survey, but part of their website also talks about ways that amateur astronomers can contribute with their own data. So it's a golden age for amateur astronomy because the equipment is so good and there's so many people doing it. I think the rough estimate is of 1.5 million in the United States alone, maybe 3 million worldwide. And there's real science for them to do.
All right, so this will be our last question for this live session, and it's kind of half philosophy and half science. And it is, if we consider free will to be real, then doesn't that mean the future is unpredictable? But then also they ask, does this mean that things like time travel and theories like the multiverse are just in the imaginations of scientists?
So the determinism of science, so it's a good philosophical question about free will and determinism and predictability and uncertainty, these interrelated concepts. Under Newtonian mechanics and Newtonian gravity, there was a sense that the universe could be predictable, that it was called the clockwork universe. It's sort of a metaphor that emerged after Newton's time, about 100 years after Newton's time. There was a sense that because we had this very precise equation for gravity, if we could just make measurements sufficiently accurately and calculate the position and motion of objects in the solar system or in the galaxy, we could just forward predict everything that might happen. And so that would take away all unpredictability from science or from the universe itself. And you know, the human variant on this is it would take away free will. It would take away the illusion or the sense that different things can happen and that we have choice over what happens. Everything's laid down by the rigid laws of Newtonian gravity and mechanics. But it turns out that Newtonian gravity is not deterministic, because as soon as you have more than two objects, which is always the situation, there are never such thing as two isolated objects in space, then Newton's law is only an approximation and you need numerical techniques to calculate it. And as we know very well from various gravity situations in the solar system and beyond, unpredictability, chaos, and instability is a common part of what happens in planetary systems, in dynamical systems. And so the predictability that was posited in Newton's time has completely gone away. It's not that things are completely unpredictable and we can't predict anything. It's just that the overall predictability is modulated or affected by episodes of instability and chaos. That can even occur in something like the solar system, where the planets formed a long time ago and they just seem to be going routinely in their orbits year after year, millennium after millennium. If you play the future of the solar system out in a computer, and I suspect in real life too, the solar system is stable but could go through some major instabilities. And it's not within our grasp to predict those, because it's not simply a matter of computer power. It's unpredictable even in principle. So modern science, and astronomy in particular, is predicated on a large degree of predictability. Otherwise, our physical laws wouldn't really be helpful to us. But there's an ingredient, there's a strand, there's a streak of unpredictability and chaos that affects all of these physical situations. And that makes the universe a very interesting place. Thank you, everyone, for your great questions. We'll be back with you in a week or two.